All right, so super cool topic for this video, implicit differentiation. As always, if you want to only see worked out problems, timestamp is in the description. At this point, it should be fairly simple for you to actually differentiate something like this. Y equals 3x squared minus 8x plus 9. Even something like this, if I were to just add a exponent here, right? Something like this you could still figure out, right? You would take the square root of both sides to get y alone. And you know what? I'll even write it like this. So you'll then end up with y equals 3x squared minus 8x plus 9, all in parentheses, raised to the 1/2 power. Same thing as doing a square root, right? So unfortunately, not all functions take this form. An equation in this form is said to define y explicitly. Basically, we can isolate y, get it by itself, right? Say you had to differentiate something that looked a little more like this. Y squared plus y equals 3x to the 5th minus 7x. Think about how you would try getting y by itself in this situation. And I'll give you a hint. You can't. At least not easily, right? You could do a bunch of work and eventually isolate y, and you'd get something super messy after doing a lot of work over a long period of time, and then trying to take the derivative of whatever this ends up in is not even something I would attempt to do, right? So we need to figure out another way to take the derivative of this, right? In this case, y is defined implicitly. We can't get y by itself, right? So in order to take the derivative of something like this, we're going to need a new technique. Luckily, that's like the point of this video. The technique is, as you can guess, implicit differentiation, right? Now, although implicit differentiation is one of the more simple topics, it seems to give a lot of students trouble. I think one of the main problems might be just the confusing notation that can be used. So I want to try to remedy that by more comprehensively defining some of the notation used. It might seem simple, but this will make these problems make so much more sense. So I highly suggest watching through this next section before looking at the worked out problems. All right, so we're going to start off pretty simple. All right, you should be familiar with this. Y equals f of x, right? They're almost the same thing, right? Y is, a y variable. F of x is a function defined in terms of x. Typically, we use them interchangeably. You should also be familiar with kind of the symbol for taking a derivative, and that would be f prime x. Okay. Now, for implicit differentiation, we don't use f of x. We use y as a variable. Just it's so much easier to use. So when I'm denoting the derivative of y, it will just simply be y prime. Now that prime there is something called Lagrange notation, right? Now, depending on the class you're in and textbooks, the textbooks you're using, you could have a different notation. There are a few different standard notations for derivatives. So something like this is equivalent to this, dy dx. That means the derivative of y, and that I said x, why didn't I write it? That means the derivative of y in terms of x, okay? What this means is, what is the rate of change of y as I change x, right? Way back, you should remember that derivatives are basically calculating a rate of change, instantaneous rate of change. And that's going to become important in a later topic, all right? So you could use, and when you're taking the derivative, I'll typically be using Lagrange notation. But I don't know if I mentioned, this is called Leibniz notation. You could continue on with this notation. These mean the same thing for this video. The reason I prefer this notation is because implicit differentiation is a crucial component of a later topic called related rates. which is an application of derivatives, like a real world type example. And writing this instead of this makes everything look so much cleaner. Okay? Now, let's just quickly talk about the derivatives. So say I have I'll use the equation from earlier. Y equals 3x squared minus 8x plus 9. And I wanted to take the derivative of this, right? The derivative would then just be y prime is equal to 6x minus 8, right? And that y prime is the derivative, right? Or this y prime could change to a dy dx, right? That dy dx equal to 6x minus 8. All right, so that's something you should already be familiar with. I'm just more kind of getting into the notation, focusing more on that right now. Now, what do we want to do when dealing with something like this, right? One thing I should also mention, when you take the derivative of y, it turns into a dy dx. When you take the derivative of x, it turns into a dx dx. That's why you don't actually end up seeing it there. It is there. It's just the same way like 1 is technically the coefficient of this x variable, but we don't need to write it. Because everything's being taken, we're differentiating in terms of x, right? We don't actually end up writing this bit. So now let's look at this example. Y squared plus y equals 3x to the 5th minus 7x. Now we want to take the derivative of this. How do we go about doing that? Here's the technique. Here's the main method. We go through the problem taking the derivative the way we normally would, but now we're doing it with two variables, right? Y is a variable and x is a variable. So let's look at this side first, the y's. Y is its own variable. So when you take the derivative of y squared, the power rule says, all right, I'm going to have 2y. Okay, now important thing, because you're finding the rate of change of y as x changes, for all of the y's that you differentiate, you need to tack on a y prime, right? Or a dy dx. So then the derivative of y should just be the constant up in front, which is 1. So that would be plus 1. And remember, we always have to tack on a y prime. Okay? And now that's going to be equal to, so we'll do this side. 3x to the 5th should be pretty easy. That's 15x to the 4th. And then 7x, that's just 7. All right, easy enough so far. Now, what we need to do is isolate y prime. Okay? I'm just going to use this sheet of paper. And the way we do that is get that alone. Now, getting y prime alone is a lot easier than if we were to try to get y alone in the beginning, right? Because this factors out. It's a GCF. So y prime times 2y plus 1 is equal to 15x to the 4th minus 7. And then I divide on both sides. Y prime is equal to 15x to the 4th minus 7 over 2y plus 1. Okay, now we have the derivative of our function, right? We have our dy dx, we have our y prime. And that's the goal of all these problems. You want to do the implicit differentiation, which means, taking the derivative of any x component the way you normally would, taking the derivative of any y component kind of the way you normally would. The extra thing you would do is tack on the y prime, and then isolate the y prime, and then you would end up with the derivative. Okay? Now let's more formally define the steps of implicit differentiation. All right, so these problems can be broken down into two main steps. Step one is just differentiate both sides with respect to x. And what I mean by that is, like, when you take a derivative, you're basically doing kind of like this. It's going to be d, and then d whatever you're taking the derivative with respect to. We're taking the derivative with respect to x, so we're doing a d dx. Now the variable that goes in here is kind of the thing you're taking the derivative of. So anytime you take the derivative with an x component, this becomes dx dx, and that just kind of disappears, which is why you don't see it there. And anytime you take the derivative with y, which is kind of the next part of step one, you put a y there, dy dx, and that takes the form of y prime, right? So anytime you differentiate a y term, multiply a y prime term to that thing, okay? So differentiate both sides with respect to x. For every y term you differentiate, multiply a y prime to that thing. And then just isolate or solve for y prime. And then whatever you get on that other side, whatever you get y prime to equal to, that's your derivative. All right? Hopefully that was pretty comprehensive, especially in the notation, and it'll make the examples more clear. Let's get into those. All right, so we'll start off simple. What I suggest you do is pause the video and try this out yourself, and then see if you got it right. All right, so step one, differentiate both sides with respect to x. And then anytime I do it to a y term, attack on a y prime. So what's the derivative of y to the third? Power rule just says, okay, 3y to the second, and now I multiply by a y prime. Minus, what's the derivative of 4y squared? Power rule again, it's going to be 8y times y prime. Now on this side, should be something you're super familiar with. What's the derivative of x to the fifth? 5x to the fourth. And then the next term, last term, is the derivative of 3x to the fourth, which is 12x to the third. Simple as that, and that's first step done. The next step is to isolate y. And doing stuff like this, it comes up a lot, this kind of being able to get something alone, which is why if you have trouble with this part, I highly, highly, highly suggest you practice something called literal equations. It's basically they give you an equation with a bunch of different variables and they say, get this one alone, isolate this variable, all right? I can't stress that enough. I tell anybody from, 8th grade all the way to whether you're 25, right? You should know how to do those. Great practice for a variety of topics. So we need to get y prime alone. Let's factor this out, the GCF, right? Way back to 8th grade algebra, 7th grade pre-algebra, whatever it is you've done. 3y squared minus 8y is equal to 5x to the fourth plus 12x to the third. Okay, let's divide the 3x to the second minus 8y. 3y to the second minus 8y, which kind of looks like g's. All right, those cancel, leaving me with y prime, which is great. Then I divide to this side a 3y to the second and an 8y, or minus 8y. And my final answer is 5x to the fourth plus 12x to the third over 3y to the second minus 8y. Now, you might look at this and kind of think that, oh, maybe I got it wrong. I have x's and y's on the same side. That's not something that's usually allowed in a final answer. Implicit differentiation, that is allowed. What's important is that you isolate y prime. As long as there are no y primes on this side and there's only a single y prime on this side, then that's good. You're golden. All right, let's check out a slightly more difficult problem. So what we got here is 3x squared plus 5xy squared minus 4y to the third equals 26. Once again, I suggest you try this out on your own. It's very similar to the last one, except you might experience a little hitch, right? This xy to the second term might cause you a little difficulty. But think about it. All right, so here, same steps apply. Differentiate both sides with respect to x. This side's easy, right? What's the derivative of 26? That's just 0. So let's take the derivative now of 3x squared. So that's going to be 6x. Now, the derivative of 5xy squared. How do we take the derivative of something where we have an x term and a y term kind of in the same place? You know what I mean? It's confusing. I don't know what exactly to do. So what we have is two different variables, two different functions, you can think of it. An x and a y squared. What do you do when you multiply two separate functions? And you need to take the derivative. Product rule. So we're going to do product rule on this thing. Okay? So imagine splitting this thing up. And there's a plus here, so I'm going to do plus and then create a little parentheses to keep this answer in. And I'll use a separate sheet of paper for this. So imagine splitting the 5xy up. So we have 5xy squared. And I split it up into a 5x times a y squared. Now, you could split it up into a x and then a 5y squared. That's perfectly valid. Just make sure you separate out those x and y terms. So what does product rule say? Well, product rule would be the derivative of the first thing times the second thing. So what's the derivative of 5x? That would be 5. Times the second thing, which is y squared. And then plus the derivative of the second thing times the first thing. Or to kind of keep it to, we'll say the derivative, or sorry, we'll say the first thing times the derivative of the second. So what's the first thing? Well, that's 5x times the derivative of the second thing, which is 2y. Y prime. Okay, remember, because we're taking the derivative of this y term, we need to tack on the y prime for this one, not this one. Okay? Super important, because here you're not actually taking the derivative of y squared to get this 5y squared. You are for this one. So let's just kind of condense it because we have some extra stuff there. So now we left with 5y squared plus 10xyy prime. All right, now let's take this, tack it in the center there. All right, 5y squared plus 10xyy prime. And that's going to be minus, this one's easy. That's the derivative of 4y to the third. That's going to be 12y to the second y prime. That y prime is super important. And that's so easy to forget. I should probably just kind of stress this. This is so easy to forget to tack on. And if you do, you will get a completely different answer. Like, it'll be wrong. And especially on, I think, like AP Calc has a multiple choice section. That's going to be annoying if that, you know, happens to be an answer choice. You know what I mean? No partial credit on that kind of stuff. However, most calc courses in college, I think, don't do multiple choice. But still, be very careful about that. So I'm going to open up these parentheses and have 6x plus 5y squared plus 10xyy prime minus 12y squared y prime equals 0. Step one's done. Now I need to isolate y prime. So I'm going to bring my y primes to one side and bring anything that doesn't have a y prime to the other side. So let's see, best way to do that, I think, would be bringing this stuff over and leaving this stuff here. So I'll subtract both sides by minus 6x and also subtract both sides by 5y squared. So what I'll be left with is 10xy y prime minus 12y squared y prime, and that's equal to 6x, minus 6x, right, because I subtracted 6x, and I subtracted 5y squared, and I end up with a minus 5y squared here. Now, this step should be pretty familiar to you, very similar to the last one, GCF on all y primes. So y prime times 10xy minus 12y squared equals negative 6x minus 5y squared. Now we just divide. And I'll just extend this so I don't have to write it twice. 10xy minus 12y squared. That cancels there, that still divides there, and our final answer is y prime is equal to negative 6x minus 5y squared all over 10xy minus 12. That's not a 12. Why am I like this? Minus 12y squared, and that would be your final answer. So the main takeaway from this example would be when you have this setup of a term that has x's and y's in it together, split it up so it's a term with x's multiplied by stuff with just the y's. Then use the product rule on them. Okay? And then after that, it becomes the same as any of the previous problems we worked on. Let's go through another example. All right, because I think the last example, that concept, that product rule concept is so important, I'm going to do an extra problem using that same concept. All right, so I highly suggest you pause the video, try this out for yourself. All right, so this first term here, let me just read this out. X to the third times y to the fifth plus 3x equals 8y to the third plus 1. All right, so the first term is an x to the third, y to the fifth. Our term has x's and y's in it. So I'm going to, on a separate sheet, we'll use the bottom of the previous exercise we did. Let's work out the product rule, right? So separate it out into something with x's and then the other thing with y's. So x to the third, y to the fifth, this is an easy one to separate out. It's just x to the third multiplied by y to the fifth. Now what is the product rule? Derivative of the first thing, which is going to be 3x squared, times the second thing, which is going to be y to the fifth, plus the first thing, not the derivative of, plus the first thing, which is x to the third, times the derivative of the second thing, which is 5y to the fourth, y prime. Okay? And then from here, let's just condense it a little, combine this stuff. 3x squared y to the fifth plus 5x to the third y to the fourth y prime. Okay? And let's substitute it in there. You don't have to do this like separately. You can build out the steps. I just want to make sure I have enough room and I'm clearly like writing out each individual line. So this becomes 3x to the second y to the fifth plus 5x to the third y to the fourth y prime. And then plus, what's the derivative of 3x? It's just 3. Equal to, what's the derivative of 8y to the third? Should be 24 y to the second y prime. Plus derivative of 1 is just 0. All right, so this is 0. Now let's get our y prime terms to the same side, everything else to the other side. The easiest thing, I think, is just to bring over this positive 5x to the third, y to the fourth, y prime, right? So let's subtract that to both sides. And then we have 3x to the second, y to the fifth, plus 3 equals 24y to the second, y prime, minus 5x to the third, y to the fourth, y prime, and I'm sure this is super familiar, GCF on our y primes. So we have y prime, 24y to the second, minus 5x to the third, y to the fourth, and that's all equal to, this stuff's the same, right? X to the 3x to the second, y to the fifth, plus 3. Lastly, I just divide, right? 24, y to the second, minus 5x to the third, y to the fourth, and then I get a final answer. 3x to the second, y to the fifth, plus 3, over 24y to the second minus 5x to the third, y to the fourth. And that would be my final answer. That's the derivative. All right, now let's look at a slightly different example. Now, I'd be remiss if I wasn't to go through an example doing derivative of trig functions, as well as exponentials, which will be the next example. These come up a lot, and I feel like they're often overlooked problems when studying. So let's look at what we have here. We want to take the derivative of x squared tangent y plus y to the 10th secant x plus sine y squared equal to 2x. All right, so let's take it one by one, right? We have all these things separating each other. We can do them one at a time. So here we have x squared tangent y. That is a term that has x's and y's in it, so we'll need to split it up and use product rule. Split up here is easy. It looks like it'll be x squared times tangent y. So derivative of the first thing times the second thing. So that's going to be, I'm pretty sure I'm going to run out of room here, but hopefully I won't. Derivative of x squared is 2x multiplied by the second thing, which is tangent y, plus the derivative of the second thing times the first thing. So that's going to end up being, the first thing is x squared. The derivative of tangent is secant squared. Cosine and sine are the easy ones to remember. Secant, tangent, all those other ones, they're kind of annoying. So just, have those memorized. So tangent y should then be now secant y times y prime. Don't forget about that. Oh yeah, I'm definitely running out of room. That's just the first one. Plus, now this term, y to the 10th secant x. It again uses the product rule. We can split this up into a y to the 10th times secant x, derivative of the first thing, 10y to the 9th times the second thing, secant x, Jesus, secant, I think the Sharpie fumes are making me dizzy, secant x, I'll just set it up like this and make sure that's in frame. Cool. Secant x, and then plus the first thing, which is y to the 10th secant, and derivative times the derivative of the second thing. Now the derivative of secant is secant times tangent. So y to the 10th times secant of x times tangent of x. And you know what? I just made a mistake that I warned you about making. Here we did derivative of the first thing, which was a y to the 10th, and I need to tack on a y prime term here. I would have gotten the completely wrong answer. So again, be very careful. I make that mistake. Okay, last term is now the derivative of this. So this isn't actually a product rule thing. It's a chain rule thing. We have an inside function and an outside function. So it's going to be the derivative of the outside function times the derivative of the inside function. So this is going to be plus derivative of sine is cosine. So cosine y squared multiplied by, what's the derivative of y squared? It's 2y times y prime. And lastly, derivative of 2x, clearly the hardest out of any of these, just 2. Okay, so now let's go about simplifying this whole thing. Why do I do this to myself? All right, so easy thing to do is we've done step 1, right? The step's basically the same. We've differentiated with respect to x. Now let's isolate y prime. Get everything with y prime to one side, everything else to the other side. Based on the y primes I have, which would be these 3 terms, it might seem easier to move everything else over to the other side. So what I'm going to do is subtract by 2x tangent y, subtract by y to the 10th secant x tangent x. Yeah, that'll be good. So then what I'm left with is x squared secant y times y prime. The next one would be plus 10 y to the 9th secant x y prime. And the last y prime term is way back here, so plus cosine y squared 2y y prime. And that's going to be equal to the stuff I moved over, so 2 minus 2x tangent y and okay, hang on. So with this kind of stuff, what I typically like to do to keep track is, all right, I use this, I use this, I used this, I did not use this, I used this, so this is going to be now minus y to the 10th secant x. Okay, and I use this. All right, so this is what I'm at now. So what you're going to do here, we have 3 terms. Each of them have a y prime in it. Factor out the y prime. And what you end up with is y prime times x squared secant y plus 10 y to the 9th secant x plus cosine y to the 2nd. And you know what? I'm going to multiply kind of this out. So it's going to be 2y cosine y to the 2nd. And that's equal to, and I'll actually just move that down because this side doesn't change at all. That's equal to 2 minus 2x tangent y minus y to the 10th secant x. Last thing is I divided all of this stuff to bring it over to the other side. And rather than writing that out, I can just go to the final answer. You should be pretty familiar with that concept of dividing to both sides. And what you end up with is a final answer of y prime equal to 2 minus 2x tangent y. Just make sure that I'm not missing a term or anything like that. Yep, I was. Here, this should have been y to the 10th secant x tangent x. I left that off, my bad. So, back to this. Yeah, 2 minus 2x tangent y minus y to the 10th secant x tangent x all over this stuff, which was x squared secant y plus 10y to the 9th secant x plus 2y cosine y squared. All right, now this was definitely a more difficult problem, and that's mainly because doing derivatives with trig functions can get pretty confusing, especially when you're doing stuff that's not only sine and cosine. When you involve secant, and that splits up into, when you take the derivative into a secant and tangent, it kind of gets hard to keep track. However, in terms of the implicit differentiation we were doing, relatively simple, I feel. We just did product rule twice, and then for this last part, we cleaned it up with chain rule. All right, now let's go through one more example. And as promised, we're going to finish off with some exponentials and this, logarithmic type of equation. So we want to take the derivative of this, same rules. Let's differentiate everything with respect to x. Now, we're going to need to be really careful here because the chain rules involved are a bit more complicated than that one in the last example. All right, let's take this one at a time. We have e to the 2x plus 3y. This is going to involve chain rule. Our inside function is 2x plus 3y. Our outside function is e to the x, or e to, just this stuff. All right. Chain rule is I think the most important thing to practice because it is the most complicated of those main early derivative rules, and it comes up a lot. It's a very common thing that just shows itself. All right. So it's going to be the outside function, the derivative of that, which e to the x is just e to the x. So e to the 2x plus 3y multiplied by the derivative of the inside function, which, what is that? That's going to be 2x plus 3y. What's the derivative of 2x? 2. What's the derivative of 3y? That's 3y, or that's 3, and then times y prime. Don't forget, we still got to tack on our y primes. Now, let's take the derivative of the right-hand side. Derivative of x squared, that's super easy, 2x. Now, derivative of the natural log of x, y to the third. This is not just a chain rule, it's also a product rule, right? We have an outside function, which is an ln of x, and an inside function, which is a x, y to the third. But then our inside function itself requires product rule. So first we'll deal with the chain rule. The derivative of the outside, that one's easy. Derivative of ln of x is 1 over x. So that's going to be 1 over what's on the inside? X, y to the third, multiplied by the derivative of the inside. Now this is where it kind of gets a little more complicated, but it's very similar to problems 2 and 3. What is the derivative of x, right? It's the derivative of the first thing, which is 1, times the second thing, which is y to the third, 1 times y to the third, plus the derivative of the second thing times the first thing. So that's going to be x times 3y to the second multiplied by y prime. Okay? Now combining all of this stuff, what we end up with is y to the third plus 3x y to the second, y prime, all over x y to the third. Okay, and then just filling this, all of this stuff stays the same, 2x, and that's equal to, I'm kind of writing this backwards, 2 plus 3y prime, and then we got over here the e to the 2x plus 3y. Okay, Now, how do we go about getting y prime alone? There are kind of a couple ways to look at this. What we want is this term, this 3xy squared y prime, to be on the same side as this 3y prime. How do we get there? Kind of a couple of different ways. One, it's going to be much easier if I'm not dealing with fractions. So what you could do is multiply this this xy to the third to both sides. That's one way of dealing with it. Here we have this multiplication, right? So I need to divide it. I'm just trying to subtract this to the other side. And what I think will be easier is to first kind of distribute this, right? So if I distribute the e to the 2x plus 3y to this stuff, I get 2e to the 2x plus 3y plus 3e to the 2x plus 3y times y prime. Okay, now I just have stuff being added together with a y prime term there. And that's going to be equal to 2x minus y to the third plus 3xy to the second y prime over x y to the third. Now, getting this y prime out is a bit difficult because we have a fraction, right? We can't just subtract and we can't just multiply. So I think it'll be easy to get rid of the denominator. Multiply both sides by xy to the third. Okay? So here we now have 2e to the 2x plus 3y xy to the third plus 3e to the 2x plus 3y xy to the third times y prime equal to, what's 2x times xy to the third? It's 2x to the second y to the third. And now that's minus y to the third plus 3x y to the second y prime. Now we just have a bunch of terms added and subtracted to each other. We can get our y primes to the same side pretty easily. I'm just going to make a swap with these two things. I'm going to take this 2e to the 2x plus 3y xy to the third over here by subtracting. Do the same thing with this 3x y to the second y prime. All right? And what I have now is 3e to the 2x plus 3y xy to the third y prime minus 3xy to the second y prime equaling 2x squared y to the third minus 2e to the 2 plus 3y xy to the third. Now, just like all the other problems, we're at this point where we do a GCF with our y primes. And on this side, we would end up with y prime times 3e to the 2x plus 3y, God, is a mouthful, xy to the third minus 3xy to the second, equal to, same stuff here. I'm not going to bother with writing that out again. And then what we do is just divide this to both sides, and our final answer ends up being y prime equal to 2x to the second y to the third minus 2e to the 2x plus 3y xy to the third all over 3e to the 2x plus 3y xy to the third minus 3xy squared. All right, so that problem was a lot, but it's really important that you take it step by step because of that. All I'm doing is following those same kind of step 1, step 2 instructions that I had printed out earlier, right? I differentiate both sides with respect to x. And that's kind of all I did there, right? And then once I got to this part, it's just a bunch of algebra to get, your y prime by itself, right? That's that first step, which typically can be the most difficult, is done in one line. This isolate y thing, or y prime thing, you've been doing stuff like that since the 8th grade, most likely. 9th grade, maybe. 7th grade, whatever. However, it can be quite frustrating. It's easy to lose track of certain variables. That's why it's important just to go line by line by line. All right, so just to quickly reiterate kind of everything we went over. Implicit differentiation. Keep in mind the kind of terms we're using, right? I, again, typically like to use y prime rather than dy dx, right? It would have been, imagine having that written for all of these. What else would be important? Right, anytime you have a term that you're trying to differentiate and it's multiplying x's and y's together, kind of separate them into two different things of x stuff multiplied by y stuff, and then do product rule with that. And always remember, tack on a y prime anytime you differentiate something with a y in it. Okay? Hopefully that was pretty comprehensive. If there are any questions, you can leave it down in the comments. I hope I made this topic a little bit easier. I went through it as much as I could. When doing practice problems, do a bunch of different types. Don't neglect the exponential stuff. Make sure to also do problems with trig functions. Super important. But other than that, that's pretty much it.